Welcome to this explainer. Today we're diving into something that's literally flipping chemistry education on its head. We're going to explore how digital platforms, specifically modern tools like PraxiLabs, are completely transforming how we teach and learn science. It's all about revolutionizing how students interact with the very building blocks of matter, making the whole learning process faster, safer, and honestly, just a whole lot more engaging. Picture this. What if you could mix highly corrosive acids and toxic oxidizers without ever putting on a pair of safety goggles? Seriously, think about it. No fear of chemical burns, no anxiety about ruining your favorite genes, and definitely no panic over causing a catastrophic spill. We all know that in traditional lab environments, there's this constant underlying friction. The physical dangers, the ultra-strict safety protocols, and just the sheer stress of making a wrong move, it all heavily limits how freely students can actually experiment, repeat their procedures, and truly learn from their inevitable mistakes. Okay, let's dive into this. To really understand the tech, we first have to ground ourselves in the core mechanism at play here: redox reactions. It's that invisible, microscopic dance of electrons between chemical species. You know the drill. When a compound loses electrons, that's oxidation. When the other compound gains them, that's reduction. It's a foundational process that literally makes so much of our natural world and our industrial processes actually function. Now, undergraduate chemistry students are expected to master this electron transfer across four main fronts: combination, decomposition, single displacement, and combustion reactions. In every single one of these instances, at least one element changes its oxidation state as electrons transfer between the reacting species. But here's the thing. Truly mastering these concepts isn't something you can just read about in a textbook. It requires serious, repetitive, hands-on practice. But actually getting that practice in the physical world, it's downright risky. Take potassium permanganate, a super common reagent. It can cause severe skin and eye burns on contact. Or diluting sulfuric acid, which releases intense, dangerous heat that can lead to terrible chemical burns. Even just inhaling iodine vapors can severely damage your mucous membranes. And let's not even talk about what happens if reagents containing chromium-6 or mercury aren't disposed of perfectly. That's a recipe for massive environmental contamination. These are terrifying physical risks, and they perfectly illustrate exactly why on-campus labs have to be so heavily restricted. So naturally, this creates a massive logistical nightmare. Traditional labs mean incredibly high running costs because you're constantly buying chemicals and paying to safely dispose of the waste. They mean strictly fixed schedules and severely restricted repetitions because, well, you simply run out of reagents. But virtual labs, they completely flip the script. We're talking zero chemical exposure, 24/7 access, and unlimited repeats right from your laptop. If you make a critical error, you don't accidentally start a chemical fire or waste expensive materials. You just hit the reset button and restart instantly. Now, what's really interesting about this slide is that number right there, 60%. Virtual labs don't just save students' skin and respiratory systems, they actually slash institutional running costs by up to 60%. When universities don't have to constantly restock hazardous volatile chemicals and shell out for specialized waste disposal, those vital resources can be redirected to other critical areas of education. It's a total win-win. But wait, this brings up a really practical question, right? In a physical lab, you're relying entirely on your physical senses, like spotting a tiny, exact color shift in a beaker or noticing a sudden solid forming. So, how can a computer simulation actually replicate those highly specific physical sensory cues so the training translates seamlessly back to the real world? Well, it all comes down to rendering hyper-precise visual chemistry. Try to visualize this. In permanganometry, you have to watch intensely for that exact moment a colorless analyte consumes the potassium permanganate, stopping only when a persistent, incredibly faint pink color remains permanently in the flask. Contrast that with iodometry, where a starch indicator undergoes this dramatic shift from a deep blue-black to entirely colorless the exact millisecond you hit the equivalence point. Modern digital tools simulate these exact color shifts beautifully, making the visual and procedural training literally identical to real life. And hey, it actually goes way beyond just watching colors change. Students get access to precise, real-time data tracking that enhances their analytical skills in ways a traditional glass flask just can't offer. They can monitor exact digital electrode potential readouts, track step-by-step oxidation number shifts as the reaction progresses, instantly see the simulated formation of precipitates, and meticulously monitor the shape of a pH curve when a titration runs under acidic or basic conditions. It's like having microscopic vision. And this is exactly where modern platforms like PraxiLabs enter the picture. They are absolutely at the forefront of bringing all these visual indicators, precise data readouts, and absolute safety benefits to life in a fully digital, highly interactive environment. Just looking at their catalog, it's honestly massive. They cover everything from the standardization of potassium permanganate against oxalic acid to the standardization of sodium thiosulfate using iodometric titration. They offer dedicated redox titration for analytical chemistry, and they even cross over into biological applications with the Alamar Blue assay. That one shows how cells reduce rhesus urine to produce a visible indigo to red shift as a measure of cell viability. So you're getting a massive spectrum of science here, covering everything from inorganic transition metals right through to complex biological assays. And this brilliantly illustrates why this software is such a game changer for university administrators. The true power of this edtech isn't just the simulation itself, it's the entire support ecosystem built around it. Students get real-time, personalized guidance from an AI lab assistant named Oxy through each step of their experiment. Instructors can build custom quizzes with automated grading baked right in. Plus, the software offers incredibly fast integration with learning management systems like Moodle, Canvas, and Blackboard. We're talking setup in as little as 24 hours. And it even provides bilingual access in both Arabic and English, allowing institutions to serve mixed language student bodies effortlessly. Now, you might be wondering, does staring at a screen actually work for learning chemistry? Well, the data is absolutely emphatic. Research published in Frontiers in Education and JMIR proves that safe, repetitive digital experimentation produces significant improvements in student comprehension, academic performance, and learning motivation. When you completely remove the fear of making a dangerous mistake and you allow unlimited, safe repetition, you fundamentally improve learning outcomes compared to traditional instruction. It's proven science. So, what does this all mean for the future? Which leaves us with one deeply provocative thought to wrap up on. If we can completely eliminate the physical danger/institutional costs by up to 60%, and at the very same time actively improve student comprehension and academic performance, is the traditional physical chemistry lab destined to become a thing of the past? It's a fascinating paradigm shift in science education, reshaping how we train the next generation of scientists. Thanks for joining me for this explainer. And I really hope this breakdown leaves you eager to explore the risk-free potential of virtual lab technology for yourself.